Welcome to the future.
Welcome to the Muxall Open Internet of Things video blog. I am your host, Michael Crane. In this follow-up to video number 30, LTC2984 Initial Power-Up and Repair, we dig into the SPI code where we are using our Espressif ESP32 system on a chip to communicate with our LTC2984 ADC. I will show you all the documents, examples, and websites I used to create the SPI code. We will also look at the LTC2984 test bench software and the C code it generates. It's pretty nice. We will look at the LTC2984 SPI specs in the data sheet, and we will go over the code and map how the datasheet specs are implemented in the software, okay? So watch video number 30 to see the SPI communication in action and the LTC2984 in action, okay? So let's get started. Okay, and for the websites that I used, I'm using the Espressif Arduino ESP32 repository for the example code. It's on GitHub, by the way, if you didn't figure that out yet. And I'm using this example right here. This it's under ESP32 libraries, SPI examples, SPI multi-buses. And I'm using this guy's example here, Alistair Simmons, I guess that's how it's pronounced. And this is pretty good. It's very well documented, or very well commented. So yeah, it worked pretty good. And I'm also using the Analog Devices GitHub, this Linduino software repository. And Linduino, in case you don't know, which I didn't really know, is LTC's Arduino. So this is, they've got a demo board, this DC 2026. And you can read about it here if you want. It's also in GitHub's Analog Devices /Linduino. And anyway, I was digging around through here for their, let's see, where is it? Is it under sketchbooks? Yeah, part number. Yeah, so 20, going to the 2000s, 2984. Here's all their other chips, 83 and stuff. Anyway, it's got all the example. These are all this is all the code for the examples. Anyway, there's a SPI library in here. I could probably search for it. Well, we'll just look at the header file. Yeah, so I actually copied some of the functions out of this. Yeah, so like this SPI transfer block and transfer word, I copied out of this and put into my code, which we'll look at here in a minute. But anyway, these, and the last website I used is this Arduino SPI library website. And this is actually kind of nice. Someone took the time to actually explain all this with the MISO, MOSI, clock, blah, 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 slave select. So in case you don't know, slave select and chip select are pretty much the same thing. I don't know why people switch between the different terms, but and maybe they mean something different, but in our case, they're exactly the same. All right. You know, it talks about the clock modes right here, whether it's triggering on the falling edge or rising, and this, so it's this SPI mode or SPI mode 0, SPI mode 1, etc., etc. And then transaction begins. This is how you set your maximum clock speed, and we'll look at all this stuff here in a minute. I didn't want to make this a real tutorial on code, because you'll see the code has just been pretty much copied and pasted from the examples and hacked together, and it's not real pretty. But I did want to show you what I was using to reference all this, right? There was one other website I wanted to point out that I used, and that was the Analog Devices website for the LTC2984. And where I said that I got that software, it's a DC2211A zip file, which basically has the schematics and had this this schematic in here. Plus, it has the Gerber files, and you can see there's a Gerber zip file. It's got PDFs of all the Gerber files. It's got the bill of materials in here, and it has everything. And for the life of me, I have been poking around this to show you guys where I got that file, and I cannot find it. And I take that back. If I type in DC 2211A, oh, did I misspell it? DC2211A.zip. Oh, that's right. I just found it a second ago. Huh. I don't know. I am baffled why I can't find this. DC 2211A. Well, I just downloaded, so if I click on design files, you can see, well, let me just do it. Yeah, you can see right down here at the bottom, it just downloaded that zip file, right? And let me refresh this. Yeah, you can see it just downloaded it again. So I can still download it, but for the life of me, I cannot find the link for it. And maybe they've got a newer version of it somewhere, but I can't find it. I thought maybe it was under this demo kit business. But yeah, I am scratching my head. I apologize. If I find it, maybe I'll post a comment under the video and let you know. Or if you find it, post a comment and let everyone know. I don't know what happened to it. But anyway, just to show you what's in it, or I kind of already did, I guess. But anyway, it's got this schematic here for the universal temperature measurement that I used. And then it's got, the bill of materials here. This is for the demo board, all right? And then it's got the Gerber files, but it also has PDFs of all the Gerber files, so you can, just take a look at all this stuff, right? This is for the demo board. It was kind of interesting. I was just using it to double check my design. And actually, like I said, I used that one PDF for laying out the RC filters on the channel inputs. So one of the things you do want to download, which I found earlier, this demo software with configuration checker and C code generation tool. And of course, the link I clicked on doesn't do anything. So, man, the wheels are coming off. Is it? Yeah, so see this install LTC2984 zip. We'll go look at him real quick. It just has this one program in it that you install, and it gives you this test bench right here, okay? And this is kind of nice. So this is here's a chip. It's got 20 channels, a COM. If you remember from the schematic, channels 10 and 9 are the cold junction temperature measurement, and 20 and 19 are. And if you go on this configuration, you can see, so differential node, yes, or a differential diode, which means you're going to use 2 channels to measure 20 and 19. We're going to take 3 readings, averaging on, yep. And these are the 3 currents it's going to use. And here's the diode ideality factor, okay? And this is actually the binary it's going to dump to the chip, right? Once you layer everything out, you can go up here. Now, if you have the demo board, check configure. You can actually run it. And since I don't have a demo board, I just create the C code. It asks me where I want to put it, and I dump it in this directory right here. And it generates these 5 files right here, right? It also, you can check the configuration, make sure you didn't do anything stupid, and it generates a C code for you. And that C code, let's pull it up real quick here. Looks like this. So here's the, we seem to be missing a file. 1, 2, 3, 4. Let's see, which one are we missing? Oh, this table coefficients. Yeah, there's nothing in this. I don't even use this. So anyway, I do use this. This is the the 2984 constants, and this is actually pretty clever the way they did this. I don't know, maybe this is common, but it wasn't familiar to me. And they're using just a boatload of define statements to configure the different types or the different parameters inside the chip. So they're using this bit shifting to build this binary word, or it's actually a double word since it's 32 bits. And they're using this shifting to set the start point inside the word. And so this sensor type least significant bit, they want to shift this this A, hexadecimal A, and they're going to shift it 27 bits over, right? So and that's how they build all this stuff. So if it's a B, and so they're going to build this double word up to send to the ADC, right down the SPI bus. So this LTC, this other file is the support functions. It's a C++ file. It just has all the support functions for like get results and measure channel and all the functions you would need to read and write to this chip. And except for what I was talking about earlier, those functions I had to get out of that library. And I'll tell you why I did that as soon as we finish this right here. So the other file is this is the file that you put in your Arduino or their Linduino, right? It's a Arduino type thing, right? So it's got the here's all the include files. Here's that LT-SPI thing we were looking at earlier. And you can see it's got a bunch of junk in here, right? And I did not want, I didn't need all this stuff, right? I definitely didn't need that. So that's why I was kind of hacking apart that LT-SPI library. I just pulled out of it what I needed, right? The other thing, so and then it also includes the the header file that we just looked at, support functions, and this table coefficients that I didn't use. So this is what goes in your Arduino. Here's the setup. And see, it's got all this junk in here. It's for setting up the I2C, this quick eval SPI init, and all this connect and the pin mode junk and all these things are not in any of these support that you get when you export that create C code from the 2984 test bench, which I didn't really like that. I mean, this is nice that it gave me the .ino, but this is a bunch of junk I don't even need, right? Well, these two I need. Discover demo board. Well, what do I need that for? Print title. Anyway, I digress. Okay, so here's what it does. So in the setup here, you're going to configure your channels. You got a couple. Here's your channel number and assignment data. And you can see it's just saying channel assignment data equals, and then here's the all the defines in this constants.h file right here get replaced. Whoops, where are we? At compile time, the compiler just replaces all this stuff with what's in this header file right here, right? So and so then they're building these. This is going to be a double word. Yeah, channel assignment's a double word right here. And then they they call a function assign channel. They're saying, okay, we want to do channel 2, which is kind of funny because channel number right here, but they never use it. I don't know why. They just plugged in 2. So, and then your channel assignment data. So they're just sending the channel number and the channel assignment data to this function here, which is assign channel. And that is somewhere around here. Let's see if we can find it. Yeah, so it does the chip select. And I actually pulled this out of mine. But so here's the channel number, channel assignment data, and the start address we get from the data sheet. And they actually do, they have this function here, get start address, is actually kind of clever. Yeah, they actually just return, you give it the base address, which is, I'd have to show you in the data sheet. I'll show you in a second here. And then times 4 because it's a double word. Yeah, so it's channel number -1 because it's zero-based counting. So you start with the base address, which is actually channel 1, right? And then you add it with 4 times 1 minus 1, which is 0. Right? So you basically just get the base address, right? We'll look at my code here in a minute. Anyway, that's the support functions for this. So this is the code that it dumped out for the configuration of which is what I have set up in my chip, right? And so you can see channel 2 is the sense resistor, right? Channel 4 is a PT1000 or PT100. And so, yeah, so it's building all this double word out of all these defined statements that's in this constants.h file. And they're just ORing everything together, right? And it's really quite clever how they did this. Like I said, it might be common, but it wasn't common to me. I thought it was fairly interesting. And if you go through this constants.h file, it's pretty big, and they pretty much have like everything, every possible configuration in here. And and that's great for compile time provisioning, if you will, but it sucks for runtime provisioning. So I'm going to probably I won't be able to use these defined statements. It won't work during runtime, right? You know, if someone in the barbecue controller changes a thermocouple type in the GUI, I can't go recompile it, right? So yeah, this isn't going to work, but this works for if you're going to have a static configuration, or if you can compile it and upload different versions of code, this works pretty good. And so it's got everything. It's basically a whole map of all the memory and all the different configurations that can be in here, like EEPROM addresses, command status register addresses. Here's that channel base we were talking about. Before we get off this is the last file is a support functions header file. It's just a header file, nothing interesting there. We looked at the table coefficients. So back to this, we're looking at this base address, channel base address. That's in the spec right here. So here's the channel assignment memory map, and here's the configuration data start address. So channel 1 was the hex value 200 right here, right? And you can see that right here. Oops, that's not it. Here it is. Yeah, so here's the base address. So the next thing I wanted to look at is a sketch. Here's a sketch that I cobbled together, and you can see I have some notes up here that I was using when I was looking through the different websites. And let's see, we can look at it real quick. So the max clock speed in the 2984 is 2 megahertz. So we'll need that when we're setting up the SPI library, the SPI library from the ESP32 libraries. All right, and that's why you can actually do what I was showing you earlier in their example, how you instantiate an instance of it. Because normally in the Arduino world, you don't do it. It just instantiates one version, and you get what you get, and you can then you after it's instantiated, then you can change all the pin IDs, right? And we can look at that real quick if you want. Here we're instantiating the modified ESP32 library, and this is just based off the Arduino library, right? But yeah, so he's just initializing a couple instances of the SPI class, and these are the defaults, right? And I'm not gonna this video is gonna be way too long if I try going through all this code. So I'm just gonna show you what I did, and if anyone has any questions, they can just ask me. But I mean, this is pretty self-explanatory, and it worked right out of the box. So it's pretty nice. The Arduino right here, when you instantiate, let's go look at one of his examples real quick. I guess either one is fine. So here, yeah, you just do a setup, and then you just do an SPI begin. And there's no instantiating the SPI. You're just calling SPI begin from the Arduino library, and it instantiates a instance of it in the background, right? Okay, so chip select is idle when high. The most significant bit is first. Clock is idle when low. Samples on the rising edge. And this is the information I got from the LTC data book, right? And these are just notes that I got from that Arduino SPI library. This is so we can set the mode later when we instantiate our version. Here's some RTD notes for the PT100 and PT1000. See, our RSense is on channel 2-1, which is, this is a hex value for that, or 0C for channel 12/11. This is for differential measurements. And these are the number of wires of the RTD. 2-wire is 00, 3-wire is 01, and 4-wire is 02. There's an excite mode, excite current, which RTD curve we're going to be using. And we don't have any custom data. And this was kind of interesting here, this note I put in right here. So this was in the 2984 data book, page 35. And it says you want to select an excite current, this guy right here, such that the sensor or the sense resistor is only about a 1 volt drop across it, right? So yeah, and that's why I was setting, you'll see later where I set this to 500 microamps or 250. I think I was in the valley of indecision, and that's because I was having boatloads of problems getting this to work at first. We'll talk about that here in a minute. All right, we'll finish the software portion of this real quick. Okay, so before we get too far into this SPI Manager tab, I just wanted to show you here's that constants.h file. I just copied and pasted it into a new tab here because I'm using this to provision the channels on the 2984. This isn't going to stay because, like I said earlier, we can't dynamically change anything, right? So before we get started, I pulled out, these are excerpts from the main barbecue controller code. So this is in the header area where we're declaring the the SPI, and what else is in here? Well, that's pretty much it. Oh, here's that constants.h file I'm pulling in. Here's where I'm just defining the max clock frequency of the ADC chip. It's 2 megahertz. Chip select zeros on pin 5. The master in slaves out is on 19. Master out slave in is on 23. The clock pin is 18. Interrupt 1 is pin 21, and the reset pin is 22. We kind of looked at that in the schematic earlier. I'm only instantiating one of the SPI classes, and then I built the base channel information, and I'm just putting in a little structure with different sizes here. It's going to have an ID, address, result, type, and config. Of course, type and config right now are just all zeroed out because we're not doing anything dynamic yet. But when we when I do dynamic information, I'm going to assign it into a channel. And here's where I just instantiate 20 basically instances of this channel right here, right? And here's the start address that we looked at earlier for channel 1. And here's the address where you get the result from. And we didn't look at that earlier, but it's basically the same thing. You just adding 4. So this is when you do a measurement test. This is where it dumps the result. And this guy right here is where you provision it. All right. And then in the setup portion of the code, in the sketch here. So this is the chip select, which is on 0. It's just an output. So I can pull it low when we're getting ready to write to the chip. And it's idle high, so I'm setting it high. And here's the interrupt. It's going to be an input because we're going to be checking it. So like when the 2984 first boots up, and it's finished booting, it'll put the interrupt high, letting you know it's done booting and ready, and it'll go low when it's busy doing something, right? Okay, and here's the reset pin. It's an output. This is so we can reset it from the ESP32, and we're going to set it low because it's active high. Correction, it's an active low reset. So I'm just setting the chip into reset mode until the ESP32 is done booting up, right? And this is also in the setup file. We're just instantiating a new class. And this means something in this VSPI means something in the ESP32 library, SPI library. And if you're wondering what that is, we can go in there, but this video is going to be way too long already. And so anyway, we're just instantiating a new class for the VSPI bus, assigning it to this variable right here, and we're telling it to begin. And we're giving it all the parameters it needs, the clock pin, the MISO pin, MOSI pin, and chip select pin, right? And then we're calling the function setup, which we'll look at here in a minute. And in the main loop right here, this is just for testing. It's just every 30 seconds, it's going to just fire off these measures. Measure channel 4, 10, 17, and channel 20 is commented out. Okay, so this is me just messing around, trying to figure out how I'm going to make this dynamic in the future. It's just a little memory map of where all this stuff is. Here's that setup that we looked at earlier. It basically just is setting the reset pin low again, which is kind of redundant, but anyway. It's going to wait for 100 milliseconds, and then it's going to go high. And then it's going to wait for 500 milliseconds for the chip to boot, which is probably 10 times longer than the chip needs, but, well, maybe not 10 times, but it's a lot longer than the chip needs. So, and this is going to go away because, like I was saying earlier, we can monitor interrupt 1, and when interrupt 1 goes high, the chip is ready to go. So this delay will get removed, right? There's some print statements, and then we're going to configure the channels, and then we're going to configure the global parameters. And then the chip will be set up, ready to go, ready to test, right? Here's the configure channels. And this is basically exactly like what we looked at earlier in this file right. Oh, where is it? This file right here, right? So this code right on the right here is what the LTC2984 test bench dumped out or created for us. And this is what I just popped in there. This is going to have to change, obviously, because it's not dynamic. And it's basically the same thing. I'm not going to go over this. I made some custom print line statements, and I'm just passing these objects in that we looked at earlier, right here, these channel objects. Okay, so this is just assigning the different channels the data, or provisioning the different channels, right? And then here's the global parameters. This is very interesting. It's just saying we're going to be using degrees Celsius. We're going to be, this is a a filter to reject 60 hertz. And then it's just going to provision it. Oh, I'm sorry, this is a print line, and this is going to just transfer it to the chip, right? Let's see, what else we got here? This is a delay in between conversions. And I was mucking around with this thing a little bit. I don't think it really needs any delay, but I added 100 milliseconds delay between conversions to give it a little chance to settle, since we put the protection circuitry in it, which is this right here. This RC filter right here is protection circuitry for the different channels, and it said in the manual, or I'm sorry, the data book, that as a little bit of a delay to let the channel settle a little bit will help with the measurements. Okay. As you can see, there is a bunch of print statements in here, and this is just that assigned channel, so we're just going to transfer our double word. This is in that define, that constants.h file is just an address, and then the channel address, we got the channel object, and we're just passing a reference into the channel, and there's the assignment data, right? Okay, and so that's basically the setup of the and configuration of the chip. I mean, it's pretty straightforward, and as you can see, most of the code I just copied and pasted right out of the the generated code by the test bench software, right? And so this measure channel right here is what's being called from the main loop every 30 seconds, or just passing in the object, channel 4 object, or channel object, and we're just telling it to measure temperature, which is also in that constants.h file and as a define statement, right? They call it convert, which is kind of odd. It's start conversion is how they say to go measure the channel, right? Okay, so when we're going to measure a channel, they call it convert channel. We're going to convert the channel, and we're just calling this function here, and he's just going to transfer this byte right here, and this is just a command to write to RAM, and we're going to write in the command status register, so we're telling it to write to this address, conversion control byte, ORed with this channel ID. And we'll go look at that real quick. It's a little bit, I don't want to say confusing, but it's not like just go start. All right. So here's the initiate conversion. Here's the command status register, and the address for this thing is 0, 0, 0. Then we got to look in the header file, but just believe me. And this is what we're going to write. We're going to tell it we want to start the conversion. We're going to set done to 0. This is nothing, and then channel selection right here, which is, this is initiate sleep. Anyway, the channel selection, which is this channel input mapping here. And so they give you examples, which is nice. So this is the 1, bit 7, bit 6, bit 5. So let's say on channel 2, let's say channel 4, which is our PT100, we want to initiate conversion, so we just send this byte with, so basically telling it to start on channel 4. And that's what this conversion control byte is, just ORed with the channel ID, which is the channel number. And that is not to be confused with the channel address, which every other command in this thing uses, except for this. So that's why I wanted to point this out, because this is a little bit of a gotcha if you don't pay attention to it. And while we're on the subject of addresses, I kind of skipped over this. I wanted to talk about it a little bit. So here's how you provision the different the channel assignments, where we did the provisioning earlier. And here's where everything is ORed together. So we'll just look at the RTD. It's a type 10 to 18. And you can go down in the spec and look that up. And this says what sense channel it is. And so if you look at the code, let's see, where is it? Okay, so here's the sensor type, PT100. It's ORed with the channel ID, and the number of wires and the excitation mode and the curve it's using, which is, if you look at this, is exactly what we need, right? Well, here's the type, which is this first one up here. The R-sense, how many wires it is, excitation mode, and the current and the curve. And this is some custom stuff we're not using here at the end. All right. And if you look down in the constants here, let me just copy this real quick. Well, here it is right here. So, and I'm not going to go through all of them. We'll just do this one right here. So here's a type, and it's just type is C for the PT100. And then we're shifting it to the least significant bit, which is 27. So if you come in here and go up 27 bits, and you can see right here is 27, 28, 29, 30, and 31 are the types. And so that's what it's doing, is just shifting everything exactly where it needs to be, okay? And it does that with all of them. So the channel assignment data will be shifted to 22, the number of wires will be shifted to 20, etc. All right, and I kind of wanted to show you that, just informational purposes. Okay, so back to this guy right here, called measure channel. We're going to convert the channel and get the results. And this is just that channel object again. And this channel output is, where it said temperature, right? So it's just the type of output is it wants, and this is just for this code right here to dump out temperature instead of voltage or something like that. So, okay, so we got the convert channel. So this wait for process to finish is, so we tell it to start measuring, right? And then we sit here and wait. And this is just a loop with a delay in it. And we're going to remove this because we can actually sit there and monitor the interrupt pin. So when the interrupt pin goes high, we'll know that it's done with the conversion process, and we won't have to sit here and just, pound the SPI waiting for this command status register to give us this result right here, which I forget what this is, 100 or something like that. Anyway, so that'll be a lot cleaner than putting these delays in. I really don't want that. So then after it's done measuring and it's ready, we just go get the results from the channel result address, and then we just print all this junk out. And we can also it also reads the voltage, and I'm not going to go through. This is straight copy and paste right out of the example. I have a bunch of debug stuff. Here's where it prints the results, and this is just more print stuff. And here's where we transfer the byte. This is just where it transfers 1 byte. And you can see, I was having so many problems with this that I'll talk about here in a minute. I've got debug stuff everywhere in here, and I left it in here because I was basically just looking at the binary. Yeah, so we can look at this real quick. So here's where we actually are using the SPI. So you can see here's our VSPI object. We're telling it to begin the transaction using these settings right here. It's kind of weird. You have to tell it these settings every time, apparently. And then I delayed it like 100 milliseconds just to kind of, let it absorb this. So, but anyway, we're giving it the SPI mode 0, most significant bit first, and our max clock frequency, right? And then after we wait 100 milliseconds, then we send the chip select low, telling the slave that we're getting ready to send it some data, and then we just send it the data, right? And then we set the chip select high, and we call this end transaction, all right? And this works pretty good, except for here's all my debug statements that I was looking at, and I don't really like code like this, but I just copied and pasted it out of an example I found, and because it took me 2.5 days to figure out what was going on. And before I get into the the hardware problem, I did want to note that this resetting the ADC right here, I needed to do this because when I originally set it up, I was setting this to high, right? Active low. I set the reset pin to high so the ADC could boot up and be ready for us to talk to it. But the SPI wasn't working at all after it was booted up, so I ended up rebooting it. So I'd set it low, then high again, and then I just change this, just keep it in reset mode until we're ready to start provisioning it, right? And that worked good. Like I said, we can get rid of this delay. But I'm still going to leave this reset. We're going to reset it, wait for 100 milliseconds, and then we'll just start monitoring the interrupt pin until it goes high, right? So I just want to point that out because the SPI wasn't working until I did this reset after this ESP32 was booted up. All right. Don't forget, you can support the Muxall Open IoT channel by donation using a credit card and PayPal, or by purchasing products at the Muxall store. Details and links are in the description under this video. Well, that's it for this video. If you liked the video, give it a big thumbs up, that helps, and hit the subscribe button, that really helps. If you have any questions or comments, post them in the comments under this video. Thanks for watching, and I'll see you next time.